phones. Remember, not all functions can be integrated. So then you have to have an approximation technique by which to solve. And that's what your calculator uses, is approximation techniques, because it cannot literally solve every single algebraic interval. Ooh, Jefferson Ing brought in an integral after his first semester of college and was like, yeah, they gave us this one, and then told us however many days later it was impossible to solve. There's multiple ones. I forget the one that he gave. You have 2 test reflections? Or test corrections? Oh, I had it due today, but then I felt like some people might not come today. And then, that's being recorded. And then I felt a little bad having it due the day after we get back from retreat when you had to make up the test. So now technically on RenWeb it says, or on your calendar it says Friday. So just throw it in your folder, yeah, whenever. Yeah. Chapter 4 corrections due Friday. Oh, it's on the backboard. Look at me. So the question that we're supposed to be answering is how instantaneous changes in rate could accumulate over an interval to produce the function that describes the total change. A ship moves along an ocean at a steady rate of 7.5 nautical miles per hour, knots, from 7 a.m. to 9 a.m. What's the total distance traveled by the ship? This is a definitely, this is a non-calculus question, or a question that definitely does not require calculus, because if it's a steady, constant rate, guys, how do we figure out how far it went? Okay, final time minus initial time, so it's traveling for how many hours? And then what? How far did it go? What? Just think, oh dear. Think dimensional analysis, the same hint that I gave Maggie with the whole question about the average cost, aka cost per item, aka dollars per item. When I have knots per hour, and we want how many miles? Knots are nautical miles. So how do we get rid of hours? Oh! How long were they traveling for? Distance equals rate times time. So if you have a constant rate, and if you have a time, then you can find a distance, right? But what is that the exact same thing as graphically? If we were to graph the constant rate, and if we were to show the time interval, wouldn't multiplying rate times time, aka making the units match, be the exact same thing as finding the area of the rectangle? Dun dun dun. We could have introduced this to you guys back in algebra. Every time you did rate times time, you're really just finding the area of a rectangle on the graph of velocity in terms of time. That's kind of cool. So then how we deal with more complicated problems where the rate is varying. We still do the same area idea, just we can't now just do times because it's going to be a different. Does that make sense? Huh. That's kind of cool. So what do we do if, example 3, why do they call it 3? I don't know, but that's okay. Example number next one. A beach is eroding at a rate of 3 cubic yards per day. How much of the beach will be lost over a year? Wait, does this need calculus? Why not? How much of the beach? What are they asking for you to have left? Yeah, they just want cubic yards. They're just looking for volume, right? How much, like the inside part. Depending on the question, it could be asking for surface area. That's a possibility, but in this one, the how muchness is going to be the volume because I see the cubic yards. So all we have to do is just multiply the rate times the time, right? But wouldn't that be the same thing as R of t and t? R of t is constant. Don't even ask. I don't know. My board's freaking out. Happens at the best times. That's a 3. That's a 365. Oh, we can read that. What happens when we do the 3 times the 365? What are we finding? Area of a rectangle. Ah! It's area again. And we end up with cubic yards. I know, I'm trying so hard. Okay. It's an R of t and a 3. Huh. Now it works. See, what was it? I don't know. I don't know. Shh. Shouldn't say that out loud. It was very entertaining in my head, though. If you want to hear what I thought. Off camera. It did tie to retreat. Anyway. I didn't say anything. I just thought it, and I was like, shh, shh, shh. That was... You can ask me after I turn off the video. Variable rates. Had to do with what might be happening on my board and who we might need. How do you find area under the curve? Why do we need it? As soon as our rates are varying, as soon as they're not constant, which we know in calculus they rarely ever are, right? So as soon as our rates are not varying, as soon as our rates are varying, they're not constant. Now we need to think about finding the area under the curve in order to be able to answer questions like how far, like how much. If we know the rates or what the rates are. To answer those questions, aka integration is net change. Oh, don't worry, not yet, not yet. We're not even integrating by hand yet, although antiderivatives randomly showed up with MVT. Anyway, wasn't random at all. If a particle starts at x equals 0, moves along the x-axis with velocity t squared, where is the particle at 3? I know you guys know how to use an integral for this, but this is the section expressing integration or answering integration type problems with finite sums or approximating with finite sums. The idea is that we are going from a left bound and a right bound, so it's a definite integral, not an indefinite integral. Geometric formulas in some senses fail us, so we go back to what we do know. What we do know is a rectangle, and a rectangle has a base and a height, yeah? Riemann sums really just come back to bases and heights. Unless we have trapezoids, then it comes back to 1/2 base times height 1 by 2. So we're going to be approximating with rectangles. But whenever we approximate with rectangles, what question must we ask? Where will the rectangle hit the curve? Where does this rectangle hit? It's all right. Where does he hit? Not there, that's above. Not there, that's below. Where does he hit? Right in the middle. And that is called what kind of approximation? Midpoint. Not as bad as you thought. How do we find the height? We plug into the function. And what do we plug into the function? The midpoint. Could we call it like x star or c or something else? Yeah. Call it x star. That was from last year. It's really awkward wording. Could also call it like c1, c2, cn for the nth subinterval. But we partition, ooh, good math term. We partition higher interval into subintervals. In each of those subintervals, we consider bases and we consider heights, and then all we have to do is add them all together, right? What makes the approximation better and better and better? More rectangles, aka bases approaching 0. Or the number of rectangles approaching infinity. I'm just seeing what's on the next page, because I forgot. Oh, got it. So the idea of this question is going backwards from velocity from 0 to 3. That's just going to be a change in position, but the change in position is from the initial. Ooh, look at that integration. Isn't that change? But we haven't specifically found definite integrals yet, so the idea is that we're approximating with our initial position, which we do know that was easy, plug in 0, and then our area, which could be a left approximation, a right approximation, a midpoint approximation, which is being modeled or shown here. They didn't give us specific details about how to approximate, so we're going to move on, but the idea is the area does find the change in the initial quantity, disregarding the time. Not disregarding, but over a certain interval of time is what I should say. So this one is specific. A particle starts at 0, moves along the x-axis with a velocity t squared plus 1, so there's my vertical shift, up 1. Where is the particle at 5? Okay, they gave us a question, but they also gave us the details that we need to give the proper answer. Remember, a Riemann sum problem on an AP test. Can you solve the definite integral? Sure. Will it be an answer choice? Sure. Will it be the right one? No. So sorry. Take some vitamins. Approximate the area under the curve using 5 rectangles. N equals 5. Of equal width, obviously, and heights determined by the as seen in example 2, aka the one that we just showed how it can hit at the middle. Guys, could I make little baby pictures with 5 different rectangles, each hitting in the middle? Sure. Does that really help me as far as solving? No. So what are we going to do? Say that we've learned this before and show how easy it can be. Sound good? Question, if I'm going from 0 to 5, how wide are my rectangles? What's my basis? Remember B minus A? Remember we called it delta x because our bases are determined by our delta x. Same thing as the base. Ignore whatever that was. So I have 5 minus 0 all over 5, but most of you logically already knew the bases were going to be by 1s, right? Fitting in 5 and a distance of 5. I could go ahead and do my A1, my A2, my A3, my A4, and my A5, and I will go ahead and plug that in for just a few of you, but that's going to help develop the idea. But couldn't we also, since we're going to be probably plugging and chugging to our calculator anyway, couldn't we also just say, hey, the area is approximately, and put it all together? The first rectangle is going to have a base of 1. Wait, they all have bases of 1, right? So if they all have bases of 1, what could I factor out of all of them? A base of 1. If this was 1/2, it'd be 1/2. If that was 2/3, it'd be 2/3. If that was 17, it'd be 17. They're all going to have the same base because it said equal width. Heights. Wait, what are the heights determined by again? Midpoint. Midpoint is the x, and how or where does the x go into to find the height? The function. Yeah, the y of the function, right? And the function being the velocity. So couldn't I do v of, what's the first midpoint between 0 and 1? Oh, 1/2. What's the next height going to be? 1 point. And then isn't it going to be? And then 7/2. Why do I know it can't go any further and I should stop? The next one's 11/2, and how high am I supposed to go? Just to 5. That's too high. Why am I writing it like this? If you're going to your calculator anyway, how can you use your calculator to do this for you quite nicely and quite easily? Yeah, couldn't your function, your velocity be y1, and couldn't you just do y1 of 0.5, literally just plug in, hit enter? Dun, 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 dun. Should you ever have more heights than you have rectangles? No. Should you ever have fewer heights than you have rectangles? No. What if it wasn't midpoint approximation? What if it was left? What would be all of our x's? 0. 0, 1, 2, 3, and because the 4 would go into the 5 and be done. What if it was a right endpoint? 1, 1, 2, 3, 4, ending on 5, or 5, 4, 3, 2, and then 1. Good. So wait, is the idea really that hard? No. But what do you have to figure out? The bases and the heights are determined by whether it's a midpoint or a left or a right. And for some of us, like this could get really messy. This one was kind of nice because it was every 0.5 since every interval was 1. But remember, you can also always do a little baby number line. 1, 2, 3, 4. Right? With the lengths of your subintervals, like I portioned it into 5, and then you can actually think of what your midpoints would be. Because some of these might get messy, and it might be helpful for you guys to make a little number line in order to visualize or to see what you're plugging in as far as the left or the right or the midpoints for each of the individual subintervals. But there you go. Yeah. Oh. Yeah. But remember the shortcut for y1 is alpha window? Alpha trace, maybe? Alpha trace, and you just hit y1. Yeah. What did we not get to in our last 30 seconds? An activity. An activity where you were going to sketch the left endpoint, midpoint, and the right endpoint, and rate the approximations from greatest to smallest. Oh, stink. Do they ever want you to know which one's bigger or smaller as far as approximations on an AP? Or whether it's an under approximate or an over approximate? So maybe we'll talk about that a little bit, but let's do it in context of the homework that you see tonight. Sound good? So you're playing with Riemann sums, but as you're playing with Riemann sums, oh, that was just a homework help example. I think that we'll probably need to look at tomorrow. As you guys do homework, are you allowed to use your calculators? Yes. But I want to see some sort of representation of what you put in, not just like, oh, hey, decimal answers I could have gotten from the back. Does that make sense? Cool. You just write the strand. Because I'll be able to read it. I'll be able to say, oh, there are their heights, there's their bases. Sweet. Is that cool? All right, go team. Yeah, in the back. I think it's on the top. Where'd you run your Sudoku? Oh. Did I give you guys a medium one or an easy one? Those of you guys doing the Sudoku. Oh, it's a medium one. Sorry. Ooh, do you want a hint for this one? You have to think outside the box, but that is not a literal hint. That's not a literal hint. Maybe you just have to think of it from a different perspective. Otherwise, it's impossible. Three odds can never make an even unless you look at it from a different perspective. Think of what I did. Test right here. Thank you, thank you. Did you figure it out? No?